Good morning, students. My name is Rakesh R, Assistant Professor, Department of Mechanical Engineering, Maharaja Institute of Technology, Mysore. This is my 7th year of teaching experience. In this session, I am going to tell what is control, action, and controllers. So, let us recall the basic closed loop control system diagram. So, in the basic closed loop control system diagram, reference input will be there. This is denoted as R of t. We will express the signals in terms of time or in terms of frequency. If it is a time domain, it is R of t. T means time. We can express the same thing in terms of frequency domain, in terms of S. So, capital R of S, that is nothing but it is in frequency domain, we will call it as S domain. So, S is replaced with J omega. Then after this is a error detector. The output of the error detector will be error signal, that we will call it as E of t. Then in order to reduce or maintain or to increase the signal which is proportional to error signal. So what we will do basically is either we will maintain proportional output or we will maintain increased output or we will maintain decreased output. So what basically we are doing is we are reducing the deviation or error signal to 0. The signal which is induced due to which, that is called as manipulated signal, or it is denoted as M of t. And finally the output, the controlled output, what we will call it as, that signal is denoted by C of t. This is a controlled output. In automation, the inputs are considered as parameter and the outputs are considered as variables. So this is C of t is controlled variable or controlled output, we can say. We need to measure the output. In order to measure the output, we will be incorporating a feedback. The output from the feedback is feedback signal, which is denoted as B of t. Let us recall it. R of t is reference input signal, E of t is error signal, M of t is manipulated signal, C of t is controlled output signal, and B of t is feedback signal. In order to quantify all those elements, we will be defining each signals in each loop. If you take an example of manual speed control, so the reference speed is around say 80 km per hour. That is the reference I need to maintain that in highway. If I cross 80 km per hour, I will be penalized. So what basically I will do is controlled output is 60 km per hour and 60 km per hour is read through speedometer. That is a feedback element. Then I will compare a reference input signal. Reference input signal is 80 km per hour. The reference signal is compared with feedback signal. So error I will calculate 80 minus 60 is 20. So my vehicle is at 60 km per hour. My desired desired input is 80 km per hour. So I can increase 20 km per hour. 20 km per hour is manipulated through acceleration or by applying brake. Here error signal is plus 20. Plus 20 means I need to increase the speed. There are several cases. Error signal is minus 20, I need to reduce the speed. Based on that, I will choose an actuation. I can accelerate or I can apply brake. In this case, I need to accelerate. I need to increase the speed. In some cases, I need to decrease the speed. In some cases, I need to maintain 80 km per hour. So these are the different types of conditions which is encountered in controller. So we need to set up an action. That action is nothing but a control action. So simply what we can say is a controller is a device which is placed in the forward path of the system. What it will do is it will measure the output variable and gives a feedback signal. This feedback signal is compared with reference input signal and determines deviation or error. And that deviation is reduced or increased or proportionally maintained. So in order to that, the deviation is reduced to 0. The manner in which the control action or control signal is generated is called control action. Simply what we can say is a control unit is a forward path which measures the output variable through a feedback and generates a signal. That signal is compared with reference input signals and determines error, and that error is adjusted to a smaller value. The manner in which this signal is generated is called as control action. The device which is used for control action is nothing but a controller. So this is the definition of control action and controller. Controller is a device, control action is nothing but it is an action what to be taken out in order to reduce the error. That's all. So while writing definition, please write both the things because both the things are interrelated each other. So before going to that, types of classification of controllers, we will see some of the property of controller which is very required in case of controlling any system. So these are the several properties of the controllers, and these are almost self-explanatory. So they are all very easy, and in order to adjust these values, we are designing a different types of controllers. The first one is error. Always error signal will be generated. Error signal is generated by comparison of feedback signal with the reference input signal. You will be measuring feedback signal by measuring the output and reference input signal. These two will be compared, and that difference will be nothing but an error. Error. Sometimes what happens, we need to adjust an error. Error can be adjusted in several ways. Here, in this case, what I have quoted manual speed control system, I need to increase 20 km per hour. Plus 20 km per hour is the error, I need to adjust it. So there are several errors. Those errors will be calculated as percentage deviation or percentage errors. So this percentage error is adjusted, and finally a controller will be designed based on the deviations. So here error is simply we can say actual output versus desired output. So this is error. So actual output minus difference desired output. Here feedback signal and reference input signal, that is the error. Next is variable range. The range is nothing but the differences between highest and lowest. Always in a control system the range is essential. Here in the manual speed control system, what is the range of error? If I go at 200 km per hour, 200 minus 80 is 120 km per hour. Will my error detector or will my controller controls that 120 km per hour, 0 to 120, will it do or not? That is a question. How much range? Here 20 km, 0 to 20. Generally variable range, the range will be varying in each cycles. That's why it is called as variable range. Based on the controller output, the range will be varying. If the controller output is beyond the reference input value, you will get a different range. If the controller output is less than reference input signal, you will get a different range. Instead of 80, if it is 90, again different. Instead of 80, if it is 60, again it is a different. So the controller should be capable of determining range in each cycle and has to adjust with the reference input signal. So that is one of the important factor in variable range. Range is maximum minus minimum, highest value minus lowest value. Here highest value can be positive value, lowest value can be negative value. It not be 0. Sometimes plus 20 km per hour. It can be minus 20 km per hour, or it can be 0. So plus 20 to minus 20. So range will be expressed in terms of plus or minus. Then controller output range. So this is variable range and this is controller output range. Again controller output range, it is almost analogous to variable range, but only the difference is what is the exact output. What is the exact output? Here also, it is expressed in plus or minus or percentage of some value. That is nothing but controlled output range. Control lag. Lag is nothing but sum of the deviation. Lag is nothing but sum of the deviation. Suppose I will measure an output 60 km per hour instantaneously. There is no control lag. The moment if I go at 60 km per hour, if I see speedometer immediately, then there is no lag. If I measure 120 km per hour and then police catches me, then if I look speedometer, then there is a lag. Lag means there is a delay in time. There is a delay in measuring the output. So this is control lag. In some of the cases, control lag is essential. In some of the cases, control lag is not essential. In some of the cases, control lag may be threat. Whenever we want to open a valve, fluid valve, in such cases, we need to give some control lag, because sudden opening of valve can increase the pressure or decrease the pressure. Because of this differential pressure, there might be delay in fluid or there might be any problems occurring in the system. So specifically what we can say is, some of the analogous input will be having some lag. Digital output will be not having any lags. So this lag we need to calculate. In some of the systems it is desired, in some of the system it is not desired. Then dead zone. Dead zone, it is the time at which the output will be zero. The output will be zero. In digital systems, this dead zone will be there in order to maintain the output to be constant. Whereas in analogous system, the dead zone or the time will be varying continuously with respect to some other quantities. So a good controller should be capable of having adjustment in error more precisely. It should adjust the error precisely, as well as the range should be more. Then it should have variable range. Instantaneously it has to detect. Then controller output range, it should measure exact output. Then control lag should not be there in any of the system. Then dead zone should be a minimum or to 0. So these are the essential property of controllers. Some of the cases the controllers will be represented through a graph. In some of the cases just it is measured analytically. Moreover, measuring the control properties of controllers is essential in order to design each controllers. Let us see the different types of classification of controllers. So there are several classification of controllers. One is proportional, integral, derivative, PI type, proportional plus integral controller, then proportional plus derivative controller, proportional plus integral plus derivative controller. The simple controller is on and off switch. On and off, or means two-way position control or two position controllers. If the switch is on, then the output is high. If you switch off, the output is low. Again, there are two values, one is 0 and another one is 1. Those two values is not varies with respect to time. That is called as discontinuous type of controller. It is not continuous, that means it is not varying with respect to time. It will give 240 volt AC at all intervals. Again, there is no delay in giving output. It is not varies with respect to time. That is nothing but discontinuous type of controller. Then multi-position. Multi-position means two-way switch, three-way switch, like that. Those are all again discontinuous in nature. Any switch will be having two positions or more position. If it is two position, it is a two position switch. If it is more position, it is a multi-position switch. These two are discontinuous control modes. Then these first three are continuous mode. In other words, we will call it as continuous control mode. So these three will be varying with respect to time. At each instant, the output will be varying. And these three are nothing but, it is composite control modes. It is a combination of two or more continuous mode. We will get composite control modes. So here the characteristics of the system will be varies in each of the cases. There is a graph. That graph will represent what is the action, what is the type of control configuration or control mode it is having. So whenever these things will be asked in the exam, first you have to write definition. After writing definition, block diagram is essential. Once if you write block diagram, we need to model the block diagram. That is nothing but mathematical modeling. We will be developing an equation which represents the physical nature of the system. That is nothing but a transfer function. It is a ratio of Laplace transformation of output variable to Laplace transformation of input variable under the initial condition 0. The transfer function will be looked in detail in module 2. So you have to write what is the transfer function. Then after writing that, there is a characteristic graph that you have to write. And then you have to list what are the specific characteristics of that control configuration. So these things you have to write whenever they ask the type of controllers. Let us see what are the different types of controllers or classification of controllers in detail. Number one is proportional controllers or proportional control action. Both are same. So the name itself indicates proportional means the output is maintained proportional to the input. So whenever they ask what is a control action, so you have to compare the definition of output of the controller with respect to input of the controller. So the definition will be like this. Proportional controller is one, a controller in the forward path which changes controller output to the proportional to error signal. Proportional to error signal, that is nothing but proportional controller. So this is M of S is proportional to error signal. This is a definition of proportional controller. When I say proportional, if I remove this proportional, I will get a constant that is nothing but proportionality constant, that is nothing but Kp. And the value of proportionality constant should be equal to 1 because it has to maintain the same output. So if you consider again a manual speed control system as an example, the reference input will be 80 km per hour, and if the controlled output is 80 km per hour, here I will measure the output or controlled variable 80 km per hour. This is also 80 km per hour. Here the error is 0. If the error is 0 means you have to maintain the output proportional to the reference input. Here in case there is no adjustment, you have to maintain the same output, same 80 in all the cases. Since we have a brain, the brain will do the control action work. Here in the system, we need to incorporate it in order to make like a brain. So what we will do is, we will make proportional controller, that is K is equal to 1. And this K is nothing but the proportionality constants. There are several proportionality constants, proportionality constant for position, proportionality constant for velocity, proportionality constant for acceleration. So Kp, Kv and Ka will be there. When we take time response analysis, we will look into what is the detail of that. So that depends on proportionality constant that will leads to steady state error. And this is a block diagram for proportional controller. Here the value of K is equal to 1. Again, making K is equal to 1 is difficult. Making K is equal to 1 is difficult. So if you make that, you will get an exact output and input. So it will be maintaining proportionally. And omega n squared divided by S into S plus 2 into omega n, this is nothing but it is a second order system. Again, let us see what is the order and type of the system in detail in time response analysis, that is module 3. Either you can take first order system or you can take second order system. When you take second order system, it is very accurate in nature, because in nature what you will be having vibrations or oscillations, those are second order in nature. When you take that, you will get exact numbers and accurate and precision answers. So if you don't know this, directly you can write plant, since just we are defining the controller type. After this, again C of S, and this is a unity feedback system. We will assume feedback as unity. The gain of feedback H of S will be 1. So this is how to write the block diagram for a controllers. Generally, this is a controller and this is a plant. If it is a proportional constant, K is equal to 1. If it is integral, integral of error signal. If it is a derivative, derivative of error signal. If it is proportional plus integral, it is proportional plus integral of error signal. If it is proportional plus derivative, proportional plus derivative of error signal. If it is all, proportional plus integral plus derivative of the signal. So this is how you have to write the definition of the controller. So M of t is manipulated output, E of t is error signal which is input to the controller, and since it is maintaining constant, the value of k you will get, it is a proportionality constant. Here output is proportional to input. If you take output by input, the value will be k, and this k is equal to 1, and this is the mathematical model, that is nothing but transfer function. So once if you know the mathematical model or transfer function of the system, we can easily obtain the response analysis. Once we know response analysis, we can say whether the system is stable or not. If the system is stable, then measure other parameters like accuracy, speed of response, oscillations, noise, etc. If it is unstable, don't measure anything. That is how we will make a response analysis of the system. If the system is unstable, we don't want that system. If it is stable, yes, it is accepted and other requirements test will be done. If it is not stable, if I switch on any fan, if it get burst, it is unstable, because we need periodic response of the system. We don't want dangerous systems. In other words, in control system we will use stability. So this is the final transfer function. Based on this, if I plot a graph, controller output versus time, since these are continuous control modes, hence it is varying continuously with respect to time, and this is linear in nature. Linear means it is maintaining same output in all cases. So this is proportional system, and maintaining this is very difficult in practical systems. By seeing this, what we can write is, it is not making any deviation, hence there is no overshoot in proportional control action. And since the value of k is equal to 1, if you have Kp, proportionality constant for displacement, if you have Kv, proportionality constant for velocity, if you have Ka, proportionality constant for acceleration, if those things exist, then we can say there is a steady state error. So this is Kp is equal to this. If it is proportionality constant for velocity, Kv is equal to S into this. If it is proportionality constant for acceleration, Ka into S square into this. So these things we will calculate in time response analysis in detail. So whenever you have a steady state error, yes, it is the system is responding for the given input or given time. Again, these systems are stable in nature because input-output relationship is linear, it is not non-linear. Once it is a non-linear, we have to calculate what is the overshoot, we have to compensate for it. So just you have to list the characters. And here less settling time indicates at 0 it is giving 0 output, at 1 it is giving some less overshoot, the deviation is not there. Stable, yes, it is a stable because it is responding to steady state error. And design of K is very proper. This is very important here. And this is a system I want this at 0th interval. After that, I don't want linearity. I want a stable output. Because at 0, it is giving some response. At 100, it will be amplifying the response. So whenever that system is there, the power consumption will be more. Hence, the design of K should be proper. And that depends upon frequency, yes. And it is impossible to maintain K is equal to 1. Hence, this proportional controller is not used in practical systems. That is the limitation. Next, let us see the integral controller. The name itself integral controller. So, a controller in the forward path which changes the controller output to the integral of error signal. Integral of error signal. So, this is nothing but integral controller. Since S is in denominator, if you cumulatively add, it will become S cube. Already there is a S square, here it is S cube. And frequency will be in denominator. And because of this increase in S, what happens means the system will be responding very slowly. That means in integral control action, it is a slow response. Hence again, it is very difficult to use integral controller alone. Like again proportional controller, it cannot be used alone. Integral controller, again it is not used alone. Because I don't want slow response of the system. Once if I switch on, the light should glow. Once I switch on, the fan should start. Once I switch on, the motor should start. Once switch on, if motor starts after 1 hour, no, it cannot be accepted. It should be instantaneous speed of response. Hence, integral controller will not be used alone. And since the S term is increasing, the system tends to become unstable. Unstable means in each cases, the output will be changing. So integral control response will be giving steady state response. And that response will be varying continuously with respect to time, and amplitude will be remaining constant. This is the characteristics of integral control system. Then derivative control action. A controller in the forward path which changes the controller output to derivative of error signal. Derivative of error signal. So whenever I write derivative d by dt is nothing but it is a time derivative. So output is responding to time derivative. Output is responding to time derivative. That means before the measurement of the output, it will give corrective action, which is not possible in practical systems. It will lead to early corrective actions. I don't want early corrective actions before measuring speed. So here, I have not measured 80 km per hour. Before that itself, it will adjust the error. I don't know what is the error itself. So, since it is an early corrective action, the derivative controller cannot be used alone. And generally, derivative controller will give transient response of the system. Transient response of the system is like that. Initially, the amplitude will be high. After that, amplitude will be decaying, and finally, it will become 0. When we take the combinations, we will see the graph in detail. And this is how the derivative response. Since it is a derivative, apply Laplace transformation, you will get S. This is S into Kd. That is the transfer function for the derivative control system. And here, as I said, it is directly measuring the rate of change of error. Since it is measuring rate of change of error, it is giving early correction. If there is no error in the cycle, here, if it corrects itself, then the system will tend to become overcorrect. Because of that overcorrectedness, the system tends to become highly unstable. I don't know what is the error. If error is 0, d by dt is also 0. But the system is not like that. If the error is 0, it will adjust d by dt. Practically not at all possible. Hence, proportional, integral, derivative controller cannot be used alone. It should be used in combinations. Either it should be used in proportional and integral or proportional plus derivative. If we used in combination, the response of the system will be stable. So this is one of the important thing in control action. So these are continuous mode. These are continuous mode. In all the cases, the response of the systems will be varying with respect to time. Here, the response of the system will be varying linearly or proportionally. Here, the response of the system will be somewhat delay in nature, or response of the system is decreased. Here, the response of the system is increased because it is responding to d by dt of the system. And whenever we say proportional control action, there are other several properties like called offset error. Offset error, instead of starting at 0, it will start at some value. So that error will be there in proportional control action because of improper design of Ki. Always the design of K will not equal to 1. That leads to offset because we are making the system to bring back its original position. We are making K is equal to 1 always at each cycles. It is very difficult in practical cases. So in the next class, let us see what are the composite control modes in detail.